Welcome back to our course, Network Analysis and Transmission Lines. So in today's lecture, we are going to discuss about the transient analysis of RLC circuits having sinusoidal excitation. So till now we have seen the transient response of RLC circuits. That means even if it is the RL circuit, RC circuit or RLC circuits. So we have seen only with the DC excitation. That means it is nothing but the DC response. We have derived the transient current expression, voltage expressions, power expressions, and the time constant expressions with respect to the DC voltage. DC, that means the source is the DC. But now we are going to derive the same kind of expressions with sinusoidal source, sinusoidal excitation. Right. So for this, we can derive the expression transient response for RL and as well as the RC with sinusoidal excitation. But those two will come as well as it's similar to your DC excitation. But whereas coming to the RLC circuit, as it is a second order circuit, why it is a second order circuit? Because it is having the two energy storage elements, inductor and the capacitor. So that is the reason why this RLC is nothing but the second order circuit. The second order with sinusoidal excitation is going to have some complex mathematical functions. So that is the reason why I have taken this sinusoidal excitation for RLC circuits. Right? So these are the outcomes of our presentation. So in this presentation, you are going to derive the expression for the transient current of RLC circuit with sinusoidal excitation, right? And also the different damping conditions, over damping, under damping and critical damping conditions. So for this, let us consider our circuit, that is RLC circuit, series RLC circuit as shown in this figure. So you can see here at t is equal to 0 minus, the switch is open. At t is equal to 0 minus, the switch is open. So let us consider at t is equal to 0, at time instance t is equal to 0, the switch is closed. So here, when the switch is closed, we can see this R, L and C is going to come into the series. Right. So in this circuit, let us consider the loop current as I, small I as the loop current. And let us consider V as our voltage source. But here this V is nothing but the sinusoidal source. Is it clear? So now for deriving the current expression, so let us know the first basic mathematical expression, how to represent the sinusoidal signal. Right? How to represent the sinusoidal signal. So let us consider, let the applied voltage is going to be equal to 1 by V is equal to Vm sine of omega t plus phi. Sine of omega t plus phi. So why I have represented the sinusoidal signal with Vm sine omega t plus phi? So this is the general form of a sinusoidal signal. If you want to know how we came across this expression, let me take a sinusoidal signal. So this Vm is nothing but your amplitude. Vm is nothing but your Vmax or V maximum amplitude of your sinusoidal source signal. As let us consider this as the sinusoidal signal. So this is going to be your Vm over here. So amplitude of the signal is given by Vm. As it is a sinusoidal signal, so mathematically it is going to represent using the sine function. So sine of omega t. Omega is nothing but your angular frequency and t is nothing but your time period. So if you consider with respect to the, so let us say this is omega t, right? Plus phi. What is this phi? Phi is nothing but your phase angle. Phi is nothing but your phase angle, right? So this is going to be our general form of a general representation of a sinusoidal signal. So that is the reason why we have considered V is equal to Vm sine of omega t plus phi. So you can consider theta also, no issue, but again theta we are considering in other way. So that is the reason why I have taken here as the phi. Phi as your phase angle. So V is equal to Vm sine of omega t plus phi. Right? So now applying as previously also what we have done, we have applied the KVL to get the basic expression. So at t is equal to 0, if you consider at t is equal to 0, if the switch is closed, so we are going to have the differential equation as, so applying KVL, what is KVL here? The EMF acting across the loop is going to be equal to the sum of the potential differences across different elements. So now, by applying the same formula or the same principle, so what is the EMF? EMF is nothing but the sinusoidal source here. So what is V? V is equal to Vm sine of omega t plus phi, which is equal to sum of potential differences. So what are the different elements we are having? R, L and C. So what is the voltage across this resistor? The current into the value of resistor. So what is the current in the loop? I is the current. So I into R plus, so L. So it is a self-inductance. What is the self-inductance here? L di by dt. Right? L di by dt plus, what is the voltage across the capacitor? 1 by C integral of I dt. 1 by C integral of I dt. So this is going to be our KVL expression for the given RLC circuit. Right. So now let us differentiate this equation number 1. So what is this equation number 1? Is nothing but your KVL expression for the series RLC circuit having sinusoidal excitation. So now differentiating this equation number 1, we can have P square plus R by L into P plus 1 by LC into I is equal to omega Vm by L into cos of omega t plus phi. How we came across this equation? So P square is nothing but the second order derivative. P is nothing but the first order derivative. So now let us differentiate this one. What we will get? I into R. So that means we are going to have R di by dt. R di by dt plus, so taking L as common, if you take L as common, what we will get? I into R by L plus di by dt plus 1 by LC is equal to, so and so, what is there here? V. So now for this, if I differentiate, if I take L as common over here, so what I am going to have? R by L into di by dt. So as it is a first order, so I have represented using P. R by L into P plus, so if you take L as common, here you are going to have only di by dt. So which is nothing but d square I by dt square. So that is nothing but the second order derivative, P square. It's multiple of I plus 1 by LC, because here if you take the derivative of integral I dt is going to become I, and here you are going to have the constant. If you take L as common, the constant is going to be 1 by LC. So 1 by LC into I is equal to, so what is the differentiation of sine theta? Sine theta is nothing but cos theta. D by dt of sine theta is going to be, the derivative of sine theta is going to be cos theta. So what is the constant here? Bm is our constant. So sin theta is going to be sin of omega t plus phi is going to be cos of omega t plus phi. But what is the internal derivative over here? Omega t. So dy dt of omega t is going to become omega, right? Omega Bm. So how we came across this L? Because here in this expression we have taken L as common. If we send this L towards this side, it is going to come into the denominator. So now here we are going to have omega Bm by L cos of omega t plus phi. Is it clear? The differentiation is going to lead this expression where p square is nothing but your second order derivative and p is nothing but your first order derivative, and 1 by LC into I is going to be equal to omega Bm by L into cos of omega t plus phi. So let it be, this is the equation number 2, right? So now the solution for this kind of equation. So what is the solution for this kind of equation? So as it is a second order non-homogeneous linear differential equation with sinusoidal function, So this kind of equation, second order non-homogeneous linear differential equation, is going to have two solutions. So one is the particular solution and the other one is the complementary function, right? Complementary and the particular. So as it is a second order, the complementary function, we can say it is nothing but your same c into e power minus pt, right? So which is going to be equal to, as we are having a two derivatives, we are going to have c1 e power minus pt plus c2 e power minus pt is going to be our solution. That is the complementary solution. So this is going to be same as your the solution of the DC response. No need to derive again. So we have already derived the solution for the second order linear differential equation with DC response. So now we should get the particular integral. What is this particular function of this equation number 2? For that, let us consider, let IP is equal to, the particular function is going to be indicated by IP. So IP is going to be equal to, so for this kind of equation with sine function, we know that IP is equal to A cos omega t plus theta plus B sine omega t plus theta. Here the theta I have considered as the phi. So similarly, IP dash, because why IP dash? Because there in that equation you can see so here, so if we consider the particular function for this, we are having di square by dt square. So it is the second order derivative, and here we are having the first order derivative. So let us take, so now let us take I is equal to, that is the particular function IP is equal to A cos omega t plus phi plus B sine omega t plus phi. Right. So for this, what is the first order derivative? IP dash is going to be equal to, derivative of cos is nothing but minus sine. So internal derivative is going to be omega. So minus a omega sine of omega t plus phi plus derivative of sine is going to be cos plus cos omega t. So here the internal derivative is going to be omega. So b omega cos of omega t plus phi. So what is the second order derivative? The derivative of IP dash. So derivative of IP dash is nothing but again, so a minus a omega is going to be constant over here. So again derivative of sine is going to be cos and the internal derivative is omega. So minus a omega into omega is going to be minus a omega square minus, so why here it is minus? Because derivative of cos is going to be minus sine, right? So that is why here minus. So b omega. So internal derivative is omega. Multiplying with that b omega square sine of omega t plus phi. Right. Now substituting these values of ip dash, ip double dash, that means the second order derivative, first order derivative, and the value of ip in the equation number 2. So what is equation number 2 over there? P square plus r by l into p plus 1 by lc into I is equal to omega bm by l into cos of omega t plus theta. So this is what the previous second equation. So this is the second equation which we are substituting in this. For second order derivative we have got it, that we are substituting here. First order derivative we got it, that we are substituting here. Right? So now substituting this, as it is the second order derivative, this omega square. So this ip value, ip double dash, the second order derivative is this, and this first order derivative is this, and this is your a cos omega t. So this is going to come over here. So I value. Right. So which is equal to as it is. So now what we have to do is, so comparing this both sides. So we are having this equation. If we compare this both sides, what you are going to have? So if we compare this both sides, so we have sine coefficients. So let us compare first sine coefficients. Later we will go for cosine coefficients. So if you compare the sine coefficients, so in this you can see, so what are the sine coefficients here? So this is the sine coefficient, and this is the other sine coefficient, right? This is the other sine one, and what is the other one? So this is the other sine coefficient. So if you compare the sine coefficients, you can see here, here you are having a minus b omega square as your sine coefficient, and minus a omega is your sine coefficient over here, and here we are having a b, right? So for this, what you are going to have? For this, what you are going to have? Which is equal to minus b omega square, as said here, minus a omega, as it is here, r by l is there, multiplication of r by l, minus a omega r by l, plus here you are having b, and the 1 by lc is your constant, so b by lc is going to be equal to 0. And simplifying this furthermore, what you are going to have? A into omega r by l plus b into, taking b as common in these two expressions, taking b as common in these two, so what you are going to have, taking b as common, 1 by lc, right, plus b if we take common, omega square minus 1 by lc is going to be equal to 0, right? So or else you can say it is minus omega square plus 1 by lc, right? So which is equal to 0. So now compare the cosine coefficients. Let us compare the cosine coefficients. So if you compare the cosine coefficients, what are the cosine coefficients over here? So minus a omega square is your one cosine coefficient. And what is the other cosine coefficient? So here b omega, multiplication factor of r by l is the other cosine coefficient. And here a with the multiplication factor of 1 by lc is the other cosine coefficient, which is going to be equal to omega bm by l. So let us write this equation. So minus o omega square plus b omega r by l plus here what is the other one? A by lc, which is equal to omega bm by l. Right. So now what we can write this one? So taking a as common in this, so we are having two expressions with a, taking a as common. So minus omega square plus 1 by LC plus B omega R by L is going to be equal to omega Vm by L. So now we are having two expressions, two algebraic expressions. If we compare this one, these two expressions we can say, so with values of A and B. Say for example, if you have A plus B is equal to 4 and A minus B is equal to 3, whether you can solve for A and B values? Yes, you can easily solve for A and B values. So now let us solve for A and B values in our expressions. So one is the equation number 3 and the other one is the equation number 4. So let us solve this equation number 3 and 4. Right. So from equation number 3, what we can write from equation number 3? From equation number 3, we can write A is equal to minus B omega square minus 1 by LC divided by omega R by L. So which is equal to, reversing this minus, so I can write 1 by LC minus omega square by omega R by L. Right. Similarly, from equation number 4, or this substitute this equation number. So the value of A, what we got over here in the equation number 4, we can have this equation. So what is the equation number 4? That is nothing but the, which we got by comparing the cosine expressions of your equation number 2. We have compared the cosine coefficients of the cosine terms, right? So now this substituting the value of A in this equation number 4, we got this expression. So from this we can write B is equal to, so we are having here Vm omega square R by L square divided by this whole term. So what is this whole term? Omega square plus 1 by LC whole square plus this one. So that means here we got the value of B. So now substituting this value of B in this equation, easily we can get the value of A. So now the value of A, you can have this one. So by solving this equation number 3 and 4, it will take little more calculation, but it will be, you should calculate very, very carefully. You should calculate very, very carefully, because here we are having how many expressions you want to know means. By solving this equation number 3 and 4, we came across the values of A, which is nothing but this, this value is nothing but your A, right? This value is nothing but your A, and this value is nothing but your B. So A and B values, you got it here, right? A and B values, you got it, right? So now substituting this A and B values, right? Substituting this A and B values, what we can come across? Values of A and B, what is the particular solution? We got IP is equal to, what is IP? We are having IP value, right? IP is nothing but your particular solution. So this IP is going to be equal to A cos omega t plus phi plus B sin omega t plus phi, right? So we got the values of A and we got the values of B. So A and B, substituting this A and B values, you came across the particular function, that is IP. So this is the IP value, particular function IP. So while you are calculating this A and B values, you should be very, very much particular. Why? Because here we are having not single variable or double variable. Here how many variables you are having? Vm is one term, omega is the other term, R is the other term, L, C. It's a complex equation. So you should calculate very, very carefully. If even single term, if you mistake somewhere, the complete solution is going to become wrong. So now we came across the equation number 3 and 4 by comparing the sine and cosine terms. So from those equations, we calculated the values of A and B, and substituting these values of A and B in our original particular function, that is IP is equal to A cos omega t plus phi plus B sin omega t plus phi, we came across this equation. So this is our final particular function. We came across the particular function. But as it is a second order non-homogeneous linear differential equation, so here you are going to have, if it is a homogeneous differential equation, obviously the particular integral is going to be equal to 0. Only we are going to have the complementary function. But whereas here we are going to have two solutions. One is the particular and the other one is the complementary. So this is our particular function. Right? Now let us derive the complementary function. What is the complementary function? The complementary function is going to be same as the DC response. The complementary function is going to be same as your DC response. But here, as it is a second order differential equation, for the DC response, we are having three different conditions. Right? So before, to simplify those equations and all, let us consider, for simplification purpose, m sin theta is going to be equal to, so in this previous expression, what we are having, so this previous expression is this one. So let us consider this as your m sin theta and this term as your m cos theta. Right? So this, for simplification purpose, I am considering this as your m sin theta and this as your m cos theta. Right? So why I am using theta here? Because we have already used phi, so I am using theta here. So let us consider m sin theta is equal to Bm omega, that is the value of A, coefficient of A over here, and m cos theta is equal to this one, B value. Right? So now we can write this to find the value of theta. For finding the value of theta, what I am considering here is m sin theta by m cos theta is nothing but the tan theta. So if we divide this m sin theta and m cos theta, we can come across this equation. Why? Because you can see this Vm and Vm is going to get cancelled, and if we simplify that, we are going to have Vm omega by L into omega square minus omega square plus 1 by LC, right? Division. So why we got this L? This is just a division, this m sin theta divided by m cos theta. We know that tan theta, which is equal to, so if we cancel this m and m, we are going to have sin by cos is going to be tan. So this equation, we simplify this, we come across this L by omega r into minus omega square plus 1 by LC. So this is going to be our tan theta expression. So from this, we can write the value of theta. So what is theta? Theta is going to be, so if we further simplify this, we can come across 1 by r into minus omega L plus 1 by omega c. So the theta value is going to be tan inverse of this value. Tan inverse of, because the tan theta is equal to this value, so theta is going to be equal to tan inverse of this value. What is that value? 1 by r into minus omega L plus 1 by omega c. So this is going to be our theta value. Right? So now if you substitute this theta value, substituting this theta value, we can write the one more form of our particular function, that is IP is equal to m sin theta cos omega t plus phi plus m cos theta sin of omega t plus phi. So this is what, right? So m sin theta I have considered is A, m cos theta is B. So A cos omega t plus theta, A cos omega t plus phi plus B sin omega t plus phi. Here we came across the m sin theta value and m cos theta value. So I am just to convert into our regular trigonometrical function, I am just modifying this equation as sin of omega t plus phi into cos theta, taking m as common, into cos theta plus cos of omega t plus phi into sin theta into m, taking m as common here. So what is this expression here? This is in the form of sin A cos B plus cos A sin B. So what is the trigonometric function for this? Sin of A plus B. What is A? Omega t plus phi plus theta, right? So you can observe this one. So this is in the form of sine A. So if we consider this as A, this is in the form of sine A cos B, theta as B here, and cos A sine B, taking M as common. So I can write sine of A plus B. What is A? Omega t plus phi plus what is B? Theta. So this is what just I am simplifying here. So here you got it. The simplifier function, much simplifier function, that is m sine of omega t plus phi plus theta. Right? So from this we can also write the value of m. However, we can write the value of m as for much simplifying. So you can simplify this one, right? So IP is equal to what we can write. IP is equal to m into sine of omega t plus phi. This is the IP value, right? Sine of omega t plus phi plus theta. What is this theta? Theta is equal to tan inverse of 1 by r into minus omega L plus 1 by omega c. So just I am substituting this theta value over here. So this theta value I am substituting here, right? So now substituting this, we came across the final particular function. But here we having the other unknown value, that is m. So let us get the value for m here. So our role is to find the value for m. This is just simplifying. For simplifying, we are extending the derivation. In different forms, we are deriving the expression for particular function. The complementary function is going to be same as your DC response, right? So just let us analyze the particular function in different ways, right? So now the next equation, however, we know that m we can write. So for simplifying, to get the value of m, so what I am writing is m as equal to root over m square cos square theta plus m square sin square theta. Whether I can write this? Yes, because if we take this m square as common in this, so sin square theta plus cos square theta is going to be 1, root over m square is going to be m. So I can write this equation. This equation is correct, right? So from this, I can easily find the value of m. We know that because we know that m cos theta value, we know that m sin theta value. Simply substituting, we can have the equation. So that if we solve that equation, we came across the value of m as, so Vm divided by root over r square plus 1 by omega c minus omega L whole square. So this is the value of m. This is the value of m. Right? Now substituting this value of m in the previous equation. What is this previous equation? That is IP is equal to m into sine of omega t plus phi plus theta. Right? This is the tan inverse of 1 by r. This whole thing is nothing but theta. Now substituting the value of m over in this equation. So we can write the particular function is going to be IP is equal to Vm divided by root over r square plus 1 by omega c minus omega L whole square into sine of omega t plus phi plus tan inverse of this one. This is nothing but the theta value, right? So this value is going to be your final simplified version of your particular solution. This is your particular solution, right? This is a little bit complex equation to remember, but you have to remember, right? So it is a second order differential equation with sinusoidal function. So you should know this one, because this is nothing new. Only the KVL equation is the key factor from the network side, remaining all your basic mathematics. Right? Differential equations, remaining all your differential equations and derivatives, trigonometry functions. Right? So this is your particular function. Right? So next we have to solve the complementary function. As I said, the complementary function is going to be same as your DC response of your RLC circuit. We know that we are going to have three different cases. One is the overdamped case. What is the overdamped case? The overdamped case is R by 2L whole square greater than 1 by LC. Right? R by 2L whole square greater than 1 by LC. So for this, we already got the equation, that is what is the solution here? So this is the complementary function for the overdamped condition, right? So what is the response for the overdamped condition could be? The response could be like, so that means it is going to take more amount of time to reach the steady state. Not more amount of time, it is going to take so this damping conditions is going to purely depend upon the value of the resistance. As it is a second order circuit, we are going to have the minor effects of the inductor and the capacitance also. Right? So these kind of equations we might come across the overdamped condition. So we know that e power alpha t into C1 e power beta t plus C2 e power minus beta t. This equation we already derived in the previous lecture. So this is your complementary function of your second order RLC circuit. Right? So for the second order RLC circuit, we are going to have the complementary function plus the particular function. So this is going to be our particular function. So this particular function I am substituting over here. So substituting this particular function, we are coming across this equation. The particular function plus complementary function is going to give your total transient current expression. So IC plus IP. So whereas IC is going to have different damping conditions, for overdamped case, this is the solution. Whereas for the critically damped case and underdamped cases, we are having. So let us get the expression for that one also. For the underdamped case, if the condition that is the R by 2L whole square less than 1 by LC, so this is what the complementary function, that is e power alpha t into C1 cos beta t into C2 sin beta t. This equation we already derived in the previous lecture. So adding up that, so this is going to be a complementary IC. This is going to be complementary IC. This is going to be complementary IC plus, and this is your particular. Just now we had derived this particular function. Right? This is nothing but m value and sine of omega t plus phi plus this is nothing but your theta value. And similarly, for the critically damped case, when that is when R by 2L whole square is equal to 1 by LC, in this condition, we can come across the complementary function as e power alpha t into C1 plus C2 t. This is the equation which we already derived in the previous lecture. This is for DC response. The same equation applies here for critically damped case. This is the complementary function IC, and this is your same, which is nothing but IP. Right? IC plus IP. We got the value of IC and IP. So adding up those IC and IP is going to be our final transient current expression. So this is what with respect to the transient response of a RLC circuits having sinusoidal excitation. Right? So thank you very much for your listening.